Okay, let's finish section 9.1. Our first, continuing on, our next theorem is called the squeeze theorem for sequences. Remember in Calc 1 you did a squeeze theorem that was limits of functions f of x. And so the theorem says, so assume there's an integer capital N such that the sequence a(n) values are less than equal to the sequence c(n) values less than equal to the sequence b(n) values for all n bigger than that big, capital N. All right, so let's stop there for a second and see what this is even saying, right? So we have, in a little n is 1, 2, 3, etc. Right? And so we have these three sequences here, a(n), c(n), and b(n). So for example, suppose a1 was here, the y value, and a2 is here, and a3 is here, and a4 is here, etc. And then if we go to the b's, suppose b1 is up here, and b2 is here, and b3 is here, and b4 is here. And then c is wherever, c1, c2, c3, c4, etc. Okay, and you keep going. Right. Notice the way I've drawn this, I don't have that b is bigger than c is bigger than 1. For example, notice here, b1 is bigger than c1, and b1 is bigger than a1, but notice c1 is not bigger than a1. It doesn't satisfy this. And I think if I go through it, I'm not going to satisfy this. What this is saying is, these can do whatever they want, but eventually, there's an integer, well, it doesn't say, well, okay, there's an integer n, such that for every little n bigger than that, right? So we don't care what happens before or at n. The a's, b's, and c's can be wherever they want. After, right, once you jump past capital N, a(n), so if the next term will be a(n) plus 1, is going to be less than or equal to c(n) plus 1, is going to be less than or equal to b(n) plus 1. And if we go over, this is at n plus 1. If we go over to n plus 2, a(n) plus 2 could be there, c(n) plus 2 could be there, but b(n) plus 2 would have to be bigger. So the b's are always above the c's or equal to, above the a(n)s are equal to. Right? So before capital N, we don't care what happens. At capital N, we don't care what happens. But after capital N, the b's are bigger than or equal to c's or bigger than or equal to a's, and that has to continue forever. Okay? So I always say, eventually this is true. Okay? So that's the way I think of this. It doesn't have to be true right away, but eventually, it could be n as a billion, eventually that has to be satisfied. That's all that's saying. Okay? So assuming that's true, eventually you get to this point where the b's are above the c's or above the a's. Then, now, this first statement is not actually in the book. I wrote this in, right? If the a(n)s are less than or equal to c(n)s less than or equal to b(n)s, eventually, the limit as n goes to infinity of the a(n) is less than or equal to the limit of the c(n)s less than or equal to the limit of the b(n). The reason why I put that in, I added that in, is because suppose you knew that a(n) was less than or equal to c(n) was less than or equal to b(n). And then by this you can take this, the limit of the a(n)s less than or equal to the limit of the c(n)s less than or equal to the limit of the b(n)s. Now suppose you knew the limit of a(n) turns out to be 12. And suppose you knew the limit of the b(n)s turned out to be 19. That tells you something about the limit of cn, doesn't it? It'd be between 12 and 19. So I added that in. It's not listed in the book. Because, if you knew this limit and you knew that limit, it tells you something about the limit of c. So I went ahead and added it in. Now what the book is saying, the actual squeeze theorem, is this. Suppose the limit of a(n) is L, and the limit of b(n) is also L. So my example had 12 and 19, which were different. It told you that the limit of c was between those two numbers. But they say, suppose both of these the limits on the outside are L. Well, obviously, what's the only way a number can be bigger than or equal to L and less than or equal to L? The limit as n goes to infinity of cn would also have to be L. That's exactly what the squeeze theorem said in Calc 1 for functions. It was, f of x is less than or equal to g of x is less than or equal to h of x. And if the limits of the outside were the same, the limit of the inside had to be the same. So it's the exact same thing that you did in Calc 1 with limits of functions, at f of x with real number domain values as opposed to sequences with integer values, positive integer values. So there's our squeeze theorem. Let me write this one here. All right, so the next example says, determine the convergence or divergence of this sequence. Well, I've mentioned in class, at least in one of them, that whenever you have a function, here I have a sequence, okay, and the numerator is trapped between two values, and the denominator either goes to plus or minus infinity, that your limit's going to be 0, that's because of the squeeze theorem. So let me actually convince you of this. Cosine pi n. All right, I'm going to, okay, so there's my formula for my sequence. Now, I'm not worried about the n squared. I'm just going to leave that alone. I'm not changing the n squared. And notice that's always positive. I'm assuming n, because it's not stated, I'm always assuming n is starting at 1. N is 1, 2, 3, 4. All right? And don't let the pi throw you. If I take cosine of anything, isn't the biggest that's going to be is 1? Remember the largest value of the range of cosine of an angle is 1. So, right? So I left the denominator alone, and cosine is no more than 1, so that's a true statement. Cosine of pi over n is always less than or equal to 1 over n squared. Likewise, the smallest cosine of anything could be, your basic cosine function, is the smallest could be is -1. So if I do this, right, I left the denominator alone, right, to make a fraction smaller, you make the numerator smaller, so that's true. Notice to make a fraction bigger, you make the numerator bigger and leave the denominator alone. So notice here I had to find, this is my Cn, I had to find the An and the Bn. Well, therefore, the limit as n goes to infinity of -1 over n squared is less than or equal to the limit as n goes to infinity of cosine pi n over n squared is less than or equal to the limit as n goes to infinity of 1 over n squared. Now what's the limit as n goes to infinity of -1 over n squared? Well, the numerator is just -1 always. -1 over 100, -1 over 1,000, -1 over billion, -1 over trillion. Those fractions are going to 0. And let's do the same thing over here. Well, when n gets huge, 1 over 100, 1 over a trillion, 1 over, whatever, that's going to 0 as well. So notice I have the limit is trapped between 0 and 0. So what's the conclusion? The limit of this sequence is also 0 by the squeeze theorem. Okay? So it's a determine convergence or divergence. So the sequence converges. So the sequence converges by the squeeze theorem. The squeeze theorem is sometimes not so easy to use because you have to figure out two sequences out here, one that's bigger and one that's smaller, that you can determine whether those, the limits of those. So sometimes it's not so easy to use the squeeze theorem. Okay? Okay, so let's look at the next topic here. It's another example. It says, consider the sequence Cn is -1 to the n 1 over n factorial. And determine, it says show that this sequence converges and then find its limit. Now I will say, the solution they give in the book, I do not understand why they're doing. They're making it so complicated. So don't look at the solution. Well, you can look at the solution in the book, but realize I wouldn't expect you to come up with that. Let's do the exact same thing that we did in the previous example. Now there's one slight little difference. Yeah, actually that's kind of the same, isn't it? Well, don't worry about it. Okay, so -1 to the n times 1 over n factorial. All right, let's find a sequence that's always larger than that and one that's always smaller than that. Well, think about, let's list a few terms. When n is 1, you get -1 over 1 factorial. That's A1, if you call, C1. It's already called C1. And what's C2? -1 squared is +1, 1 over 2 factorial. And then C3, we're back to a negative, that's -1 over 3 factorial. So you see the pattern. So it alternates. This is an alternating sequence. You get a minus, a plus, a minus, a plus, right? But if you just ignore the minus for a second, right? If I just put 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, isn't every single one of these going to be less than or equal to those? Notice for the even subscripts, they're exactly equal. For the odd subscripts, this one's even, this one's negative, and that one's positive. So clearly that's less than equal to that, that's less than equal to that, etc. So if you just drop the negative 1 to the n and say 1 over n factorial, that's a true statement, right, from what I was observing here. Now, on the other hand, okay, now I want something that's always smaller than all of these. Well, instead of ignoring the negative to get the plus, what if I put a negative on every single one? Notice when the subscript is odd, they are equal to each other. And notice now this one is negative and that one's positive. So every single one of these, if you keep the negative, every single one of these will be less than equal to that. So if I keep the negative on 1 over n factorial, that will be true. So that's the same flavor of the last one. But I use the fact that cosine was trapped between -1 and 1. You know, I'm basically using the fact that negative 1 to the n is trapped between -1 and 1. It's the exact same idea. Okay. Again, this isn't what the book is doing. And so, therefore, the limit as n goes to infinity of -1 over n factorial is less than or equal to the limit as n goes to infinity of -1 to the n 1 over n factorial. Less than or equal to limit as n goes to infinity of 1 over n factorial. So again, we're interested in this limit, the one in the middle. Right? Well, when n gets huge, what happens to n factorial? If n gets huge, n factorial is huge. And so 1 over that very large number, when n gets bigger, is going to head to 0. Now, same thing down here. I mean, we can pull the negative out front. That was one of the properties of limits of sequence. When you have a constant times something, you can pull a constant out front. And we just said the limit of that was 0, so negative 0 is still 0. And notice our conclusion. The limit as n goes to infinity of -1 to the n of 1 over n factorial is 0. And therefore, our sequence converges by the squeeze theorem. Okay. So I think the motivation in the book of why they're doing it this strange way is because you haven't worked with factorials, and so they're changing it to something that you're a little more familiar with. But I think it's obvious if you have 1 over n factorial and n gets large, 1 over that is going to 0 because it's 1 divided by a number that's getting huge. So I think that's why they're doing that, but it seems to me it's obvious that this goes to 0 when n goes to infinity. Okay, now the next theorem can be useful because sometimes these negatives, you know, this is an alternating sequence. It's negative, positive, negative, positive. Sometimes that's not so easy to work with, depending on the sequence. So the next theorem is called the absolute value theorem. It says if the limit as n goes to infinity of the absolute value of an is 0, then the limit of the sequence without the absolute value goes to 0. Right, now be careful, it's not necessarily true the other way around. If the limit of an equals 0, that doesn't necessarily mean the limit of the absolute value is going to 0. I say. I may have to think about that, but be careful. Use the theorem in the correct order, okay? If this is true, then this is true. Okay? Okay, so let's look at this example we just did, right? It says to do it again, yeah, right? So let's look at Cn. So Cn is that, I'm not going to write it again. Let's take the absolute value of Cn. Well, 1 over n factorial is always positive because we're assuming n is 1, 2, 3, etc. That's either plus or minus 1, so the absolute value of that's going to be 1, so it's just 1 over n factorial. So that's just the absolute value of Cn. Now let's take the limit of the absolute value. So the limit, as n goes to infinity, of the absolute value of Cn, that's the limit as n goes to infinity of 1 over n factorial, and we already discussed that's 0. Right? So by the theorem, if the limit of the absolute value of the sequence is 0, that means, so the limit as n goes to infinity of the original formula, minus 1 to the n 1 over n factorial is 0. You prove this with the squeeze theorem. It's basically what we did before. You can prove this theorem with the squeeze theorem, so I assume, yeah, sure. Okay, so you don't really have to write out the squeeze theorem, but notice this is only true if this is going to 0, okay? So if this is going to 3, you can't use the theorem in the same way. Oh, that goes to 3, that goes to 3. You have to be careful. Okay, so if the limit of the absolute value of the sequence is 0, that means the limit of the original sequence was 0 as well. Okay, so let's shift gears a second for these next two examples. I mean, here we were given a formula for the sequence, so you can plug in 1 and 2 and 3 and 4 and list the terms. What if, on the other hand, they give you a list of terms and it would be helpful to find the formula? Again, sometimes those aren't so easy to do. So the next example says, consider the sequence 1, negative a fourth, 1/9, negative 1/16, dot, 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 forever. So it goes on forever. So it says, write an expression for the nth term. Find the formula, a sub n, if we call this sequence A. Okay, so we want a sub n. Now, what I usually do, especially if I've noticed all these are fractions, and then I have 1. 1 seems out of place here. So what I try to do is ignore ones that look out of place, look at the other ones, try to come up with a formula for those, and then once I do that, see if the formula I came up with makes sense for 1. Okay, so I look, ones that are simplified or don't look quite the same, I just ignore them, try to come up for a formula for the rest. Now what's happening, I always look at the pluses and the minuses first. Notice it's plus, minus, and the pattern, it's implied the pattern continues. So it's just like the one we were doing a second ago, right? When you have an alternating sequence like that, a sub n, you're going to need -1 to a power. Right, that's what it had to say. Now I usually just say, well, let's put -1 to the end, and then see if it works. Okay, so again, if it's not stated, I always assume n starts with 1. So if n is 1, I get -1 to the 1 and it doesn't work. If n is 2, I get -1 squared and it doesn't work. Well, we're off. So all you have to do is just change it to n plus 1 or n minus 1. I usually just put plus 1. Notice now when n is 1, I get -1 squared is plus 1. When n is 2, I get -1 cubed, which is minus 1. And so now it works. So if you have an alternating sequence, it's either -1 to the n or -1 to the n plus 1. Try one of them, and if it works, great. If it doesn't, try the other one. Okay, so now, again, ignore the -1, ignore the negative signs, because we've got those taken care of. We have 1/4, 1/9, 1/16. So it looks like the numerator is always 1. That's no problem. Now, what's the pattern in the denominator? 4, 9, 16. Well, 4 is a perfect square, 9 is a perfect square, 16 is a perfect square. Okay? So notice that this is the second term, and notice it's 2 squared. This is the third term, and it's n cubed. This is the fourth term, and that's, I didn't mean cube. It's the second term in 2 squared, the third term in 3 squared, the fourth term in 4 squared. So it looks like it's n squared. Now let's check the ones we just did. Okay, so when the n is 1, this is n is 1, this is n is 2, n is 3, n is 4. So let's check those. So when n is 2, I get -1 cubed, 1/4. When n is 3, I get -1 to the 4th, that's plus 1, 1/9. And when n is 4, I get -1 to the 5th, which is -1 over n is 4, 4 squared 16. So that works. Now let me go back and see if what I have makes sense for n equals 1. When n is 1, I get -1 squared is plus 1, 1/1 squared is 1. We're good, so that's a valid answer. Now if for some reason you come up with a formula and you're not starting at n equals 1, again, if you just write this, I'm assuming you're telling me n starts with 1. If you came up with a different formula and you needed to start with, say, n is 0, you should write n greater than or equal to 0 out there for me, so I know you're starting. This makes no sense here, obviously. But if you came up with a different formula, but you weren't starting at 1, tell me you're starting at another place. Or sometimes you may come up with a formula and you have to start at 3. Okay, so just make sure you tell me that. If you leave it off, I'm assuming you're starting at 1, just like I did here. Okay, let's do another one. The next one says, do the same thing, come up with a formula, and the sequence is 1x, x squared over 2, x cubed over 6, x to the 4th over 24, and they give one more, x to the 5th over 120, dot, dot, dot. Again, the 1 and the x seem out of place here compared to the other terms, so I'm not going to look at those. So I would call this one b sub n, just to call it something different, okay? So, well, let's look at the powers. You have an x squared, an x cubed, x to the 4th, x to the 5th. So the powers are just increasing by 1 each time. Now here, we have to be careful here. So this is n is 1, n is 2, n is 3, n is 4. And those aren't really matching, right? Right. So you could say, if n is 3, the exponent's n minus 1. And if n is 4, the exponent's n minus 1. And if n is 5, the exponent's m minus 1. So I'm going to do it like that because I've labeled it. I will do it another way in a second. So I'm going to write n to the x to the m minus 1. Again, check with what I have. When n is 3, you get x squared. N is 4, you get x cubed. N is 5, you get x to the 4th, and we're good. Okay, now what about the denominators there? How are we getting these numbers from those? I mean, it's not like it's not an obvious square or cube or something. Right? So what you might want to do, because I recognize these numbers, right? 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 3 times 2, which is 6, 4 factorial is 4 times 3 factorial, which is 24, 5 factorial is 5 times 4 factorial, which is 5 times 24, which is 120. Those are factorials, I recognize them. So you might want to get familiar with the factorials because they pop up. Notice in the previous example, I know when you saw 4 and 9 and 16, you knew they were perfect squares right away. So you should probably get familiar with the factorials. Okay, what's 6 factorial? It's 6 times 5 factorial, so it's 6 times 120, which is 720. Okay, so you probably want to get used to the factorials. Now notice, this is 2 factorial, this is 3 factorial, that's 4 factorial, 5 factorial, which is 1 less than each of those. So the denominator here is n minus 1 factorial, right? When n is 3, that's 2 factorial. When n is 4, that's 3 factorial. When n is 5, that's 4 factorial. So that's working for all of those. Let's go back and see if it works for the first 2 terms. So when n is 1, I get x to the 0, which we interpret as 1, over 0 factorial, which is 1. 1 over 1 is 1. When n is 2, we get x to the first, and 1 factorial is 1. So it's x over 1. So they do work. So look at these that have the similar form, come up with the pattern, and then make sure the ones that don't seem to fit satisfy. Now that was kind of hard to do that one. Okay, so let me do it again in a different way, just because the numbers didn't quite match, okay? What if I did this instead? What if I said this is n as 2, this is n as 3, this is n as 4, this is n as 5, so then the 5s and the 4s and the 3s and the 2s match, which makes that n as 1, and this is n as 0. Again, you don't have to start with 1, that's just a standard thing to do. So if we do this problem again, notice the numerator is x to the n, x squared, x cubed, x to the 4th, x to the 5th. And what's the denominator? 2 factorial, 3 factorial, 4 factorial, 5 factorial, so it's n factorial. Now if we back up, when n is 1, we get x to the first over 1 factorial, that's x. And when n is 0, we get x to the 0 over 0 factorial, which is 1. But notice here, you're going to have to tell me that you're starting with n as 0. Okay, that's what I was talking about in the previous example. So either solution, the one I had or this one, I'm perfectly happy with. Notice this one's easier to figure it out because you don't have to do that shifting with the number. Okay? Okay, so now we have 2 more definitions, and then the rest of the problems are related to these. So a sequence is called monotonic if its terms are non-decreasing. Notice that's not the same as increasing, or non-increasing, which is not the same as decreasing. So in other words, A1 less than equal to A2 less than equal to A3 less than equal to dot dot dot. So notice, these are not increasing because A1 could equal A2. That's not increasing. But notice we say it's non-decreasing because the terms are not getting smaller. Okay? And so this is non-decreasing. And likewise, what's non-increasing? Okay, that's not the same as decreasing because we're allowing equality. Okay, so A1 is bigger than or equal to A2, so they could be equal. But notice they're certainly not getting any bigger. They may not, A1 could equal A2, could equal A3, could equal A4, so they're not decreasing, they could all be equal. Okay, so that's the definition of a monotonic. So if your sequence either does this or does that, one or the other, we say it's monotonic. Now you can't do A1 bigger than or equal to A2, and then A2 is less than A3, okay? That wouldn't be monotonic. You can't mix. So it's either all of those do that or all those do that. That's monotonic. Okay? The next definition says, a sequence is bounded above if there's a real number capital M such that a sub n is less than or equal to m for all n. So every value of the sequence always less than or equal to m. So again, so I'm just assuming m is some positive number up here. It's not a horizontal asymptote, I'm just drawing it in so I can see it. So here's a1, here's a2, n is 1, n is 2, n is 3, n is 4, etc. So a1 is here, a2 is here, a3 is here, a4 is here, right? Now what if a5 is up here? Right? Now, so this m is not an upper bound, right? To be an upper bound, all the values of a have to be below m, okay? Now, be careful though, it says there is an m for which this is true. So suppose every value after this was below m. Right? Suppose every value of a was below this line, but a5 was above. Does that mean that the sequence is not bounded above? No, because let me change the m. Don't choose that for the m. Put the m up here. Now all of these were already below, and now this one is too. Okay, so it says there is an m for which all the values are below. Okay, so you can put m wherever you want. Okay. So what would it mean if it's bounded above? If you weren't bounded above, what would your sequence have to do? It could do this, and then one's above, right? But then you can move the m. So what has to happen to not be bounded above? Your sequence has to just keep getting bigger somewhere along the line. I mean, it could do this. It could go Notice I'm getting bigger. They don't have to get bigger sequentially. You could do everything in between, but eventually you just have to have values that get bigger along the way. That would be not bounded above. Likewise, bounded below just means you can find another number, what are they calling here? N, capital N, where all the values of the sequence are above. Okay? So bounded above means you can find a number that's bigger than all the values of the sequence. Bounded below means there's a number that's less than all the values of the sequence. Okay, a sequence, the m is called the upper bound, the n is called the lower bound. A sequence is bounded if it's bounded above and below. In other words, you could draw a horizontal line here and a horizontal here, and every value of the sequence is trapped between them forever. Okay, so that's bounded. So bounded above, bounded below, that's the upper bound, that's the lower bound. Bounded is trapped between. Okay. Now, a nice theorem, notice we talk about monotonic and we define bounded. The theorem says if a sequence is bounded and monotonic, then it has to converge. So if you're given a sequence and you can figure out that it's bounded, notice it's bounded meaning both above and below, and monotonic, then you know the sequence converges. So instead of trying to figure out taking the limit, doing convergence that way, you could just prove bounded and prove monotonic. So to illustrate these ideas, I say, give an example of a sequence that's bounded but diverges. Bounded but diverges. Could you give me a formula? So bounded means every value is trapped between two numbers, above and below, but the sequence doesn't converge. Now obviously the sequence can't be monotonic, because if it's bounded and monotonic, the theorem says that we would have convergence. So can you think of a sequence that would be trapped between two numbers, like it's trapped between, but it doesn't have a limit? Can you give me the formula of one? Well, I drew that, so you can visualize and see what's going on. We did an example, I think in the first video. What about cosine n? Right? Remember we showed that cosine or sine in the other lecture doesn't converge because it keeps doing this thing. Notice it's trapped between -1 and 1, right? Cosine is always between plus or minus 1. But we saw in that other thing that the points just go all over the place. They don't start approaching as soon as they get it, and then they turn around. So there's an example of a sequence that's bounded but doesn't converge. So bounded, it doesn't get you convergence by itself. Just having bounded isn't enough. If you have bounded and monotonic, then you're good. Then the second one says, B, let's come up with a formula for a sequence that's monotonic but diverges. So again, if you just have bounded, that doesn't give you convergence. If you just have the monotonicity, that doesn't give you convergence. But if you have bounded and monotonic together, the sequence has to converge. So can you think of a sequence that's monotonic? So it's non-increasing or non-decreasing. So you can't start getting bigger and then turn around. You can get bigger and then go horizontal and then get bigger again, right? You can have equals to, but you can't go up and then go back down. Or you can't go down and then come back up. That wouldn't be monotonic. Well, what's an easy example, right? You just have to keep getting bigger and bigger and bigger. How about n? So 1, 2, 3, 4, 5. It's monotonic, right? It's non-decreasing. In fact, it's increasing, right? You keep getting bigger. It diverges because you don't approach a single number. It just keeps going up forever. Right, so there's some example of some sequence that satisfy each of those. I mean, I could put in squared here. It's monotonic, but still diverges. Okay, let's look at this next example. They give a sequence, and they say, determine whether this sequence, a sub n is 3n over n plus 2, is monotonic. And then discuss the boundedness. Now, if I don't have a good feeling for the monotonicity, does it keep getting, is it non-increasing or non-decreasing? Pick a few values and plug in and see what happens, okay? Because if you plug in and you get bigger and then it turns around, you've ruined the monotonic part, okay? Right. So if you do that here and start plugging in numbers, you'll see that it appears the sequence is monotonic. Now, just because you look at the first 5 terms doesn't mean anything. It could keep getting bigger, or non-decreasing, for 1,000 terms and then turn around, okay? So just looking at the first 3 or 4 terms isn't enough. Now, I chose this example to show you a technique that may help you. Okay, I read that, okay? Let me write this in terms of f of x, 3x over x plus 2. And I'm assuming x is bigger than or equal to 1 because the domain of the sequence is n is bigger than or equal to 1. Now, why am I doing that? Because remember, every single one of these, if I graph this, it's some nice, it's a rational function. Notice the domain is x not equal to -2, so that's not in that, in my domain here. Okay, so this is going to be a nice continuous function for 1 to infinity. And notice this sequence will sit on that function, as I discussed before. Okay, so I want to do something with this function. Let me take the derivative. So I hope you understand why I rewrote it, because we're not used to thinking of derivatives of sequences. I mean, that technically doesn't make sense. So I rewrote it as a function. So it's quotient rule, bottom, derivative of the top, minus top, derivative of the bottom, all over the bottom square. Okay? So bottom derivative of the top, minus top derivative of the bottom over the bottom square. Let me simplify. I get 3x plus 6 minus 3x. 3x plus 6 minus 3x. So I'm just getting 6 over x plus 2 squared. Okay, no problem. What can you tell me about the expression 6 over x plus 2 squared? Again, we only need for x greater than or equal to 1. Can you tell me anything about this expression, 6 over x plus 2 squared? Well, remember, x plus 2 isn't going to be 0, so that's not a problem. When you square the denominator, you're always going to get a positive number. You're not going to get 0 because we're not allowed x to be -2. This is always positive, isn't it? Right? If x is at least 1, x plus 2 squared is always positive, and 6 divided by that will be positive. And notice what I have. The derivative of this function is always positive. If a derivative is always positive, what does that tell you about f? That tells me f is increasing. Remember from Calc 1, if the derivative is positive, the original function is increasing. Well, if this function is increasing, that means the sequence is increasing because the sequence is on top of the function. And therefore, what does that tell you about an? Hence, the sequence an is monotonic. I mean, it's better than non-decreasing. It actually is increasing, so there's not going to be any ties. The sequence is actually getting bigger each time. It's not going to get bigger and then have a tie. Okay? So this is a way you can show a sequence as, well, if it pops out and it's clear that this is always positive, or if this had been always negative, it'd be monotonic because it would be decreasing either way. So just keep that in mind. I mean, if you have a sequence and you can't, you know, and it looks like the values are getting bigger, it looks like the values are getting smaller, and you're just not sure how to show that, try rewriting it as a function f of x and taking a derivative. If your derivative is always positive on the domain or always negative on the domain, you're going to have the sequence is monotonic. So keep that in mind. That's one method. Okay? Now, the other part said, let's talk about the boundedness. Right? So, clearly, which is a dangerous word in mathematics, a sub n, which is 3n over n plus 2, is greater than 0. Do you agree? Remember, n is 1, 2, 3, 4, 5. Positive over positive is positive. So this is always bigger than or equal to 0. So 0 is a lower bound for the sequence. Right? So if I were to, sketch this, again, I'm not saying it's a horizontal asymptote. So there's 0. I know these are A1, A2, A3, A4. Oh, it doesn't do that. We just showed it's monotonic. So A1, A2, A3, A4, right? It's doing that. Okay? So 0 is below all of them forever. So 0 is a lower bound. Okay? Now, for the upper bound, note that we talked about this, what I'm about to do here, when we were doing the error term in the trapezoidal rule. So let me write a sub n, which is 3n over n plus 2. Remember the game we played there? To make a fraction bigger, you can make the numerator bigger or the denominator smaller. So if I wanted to make this bigger, I can make the numerator bigger or the denominator smaller. I'm going to make the denominator smaller by just taking out the plus 2. Right? I left the numerator alone and I took out the plus 2. So I left the numerator alone, I made the denominator smaller, and they're still positive, right? If I change that to a negative, it's going to be a different story, right? But to make a fraction bigger, I made the denominator smaller, so this is a true statement. But notice what this turns out to be, that turns out to be 3. So what I just showed was a sub n is always less than 3. So what I just showed is that 3 is an upper bound. So they are getting bigger, but they're not going to get bigger than 3. That's what I showed. So 3 is an upper bound, and and the sequence an is bounded because I got an upper bound and a lower bound. Now remember the question. It says determine whether the sequence is monotonic. We did that. Discuss the boundedness of the sequence. The sequence bounded. You can have a sequence that's bounded below but not bounded above. So it would not be bounded. It'd be bounded below but not above. A sequence can be bounded above and not bounded below, which means it wouldn't be bounded. Okay, so we did that. Now, what can you conclude about this sequence? It didn't ask for it, but what can you conclude? The sequence was monotonic and bounded, which means the sequence must converge. Okay. Another way you could have done this one, let me show you. Instead of making the denominator smaller, we could have made the numerator bigger. Now, what you want to do there to make the algebra work out, because remember, when you're doing boundedness, you don't want a number, you don't want 3n, you have to get a single number, not an expression. Okay, so not 3n or 2n or 2 over n, you want to get a single number. So what I would do here on this one, just to make the canceling, I would add 3 to the numerator. If you're not sure why, you'll see, right? To make a fraction bigger, I left the denominator alone, I made the numerator bigger. But notice you can factor a 3 out of the numerator now. The n plus 1's cancel, and you get your 3. That's why I added 3, so I could factor it out and cancel. So I could have done the same thing that way to get the upper bound. Okay, the next example, number 60, it says, let's look at the sequence an, which is cosine n over m. It says determine whether the sequence, this one, is monotonic. Determine if it's monotonic, okay. Now, just because it's cosine n, and we've seen that, it doesn't seem to me that that's going to keep getting bigger or smaller. So let me just plug in some values. I am in radian mode. If I do cosine of 1 over 1, I get about 0.5403. A2 is cosine of 2 over 2. I get negative 0.2081. Right? So it looks like I'm getting smaller here. If I do a 3, it's cosine of 3 over 3. which is negative 0.33299, so I'm just going to say 33. Okay, I'm getting smaller. If I do a 4, I get cosine of 4 over 4, which is negative 0.1634, and notice I've gotten larger. So that's how you can show a sequence is not monotonic. Show that it gets smaller and then bigger, or bigger and then smaller. Now, frankly, I mean, you don't even have to write I just did the first two just to start hunting. Once you, on scratch paper, once you do that, oh, I didn't mean to do that. That's not enough. Let me put the A2 back. Negative 0.33. No, sorry. A2 was negative 0.2208. What, something like that. Right, okay. So you have to have three values. So notice I got smaller and then I got bigger. So you don't need A1 because that didn't have anything to do with it. So once you figure out where you go smaller and bigger or bigger than smaller, you only need three values. So since this is true, right? Since that's true, AN is not monotonic. To show a sequence is not monotonic, like I said, just find three values in a row where you get bigger than smaller or smaller than bigger. That's all you have to show. To show monotonic, to show monotonicity, you have to do something like we did before, like with the derivative, or convince yourself you're always going to be getting bigger or smaller. Then it says discuss the boundedness of the sequence. Okay, so now I'm trying to show that this is always less than or equal to a number or bigger than or equal to a number. Cosine n over. Now we saw, right, sometimes cosine n is positive, sometimes cosine n is negative. So these are, this whole thing is sometimes positive, sometimes negative, right? Well, let's do like we did before. We know this is always less than or equal to 1 over n because cosine is no more than 1. We know it's bigger than or equal to minus 1 over n, right? I left the denominator alone. Cosine's trapped between plus or minus 1. Now, what I mentioned before over here, 1 over n is not a constant. Okay, 1 over n is not a constant. So I can't say, oh, it's bounded above, but it is. I mean, it's always less than or equal to 1 over n, but that's not a bound because it has to be a number. Well, what can you tell me about the expression 1 over n? If n is 1, you get 1. If n is 2, you get a half. If n is 3, you get a third. The numbers are getting smaller, so isn't this always less than or equal to 1? 1, a half, a third, a fourth, a fifth, a sixth. Likewise, over here, you get negative 1, negative a half, negative a third, negative a fourth, right? Negative 1, negative a half, negative a third. Well, that's not quite right. Negative a fourth, negative a fifth, negative 6. So notice the smallest number is always negative 1. So with that argument right there, I use the cosine to get that, and I just use the fact that, well, 1 over n gets smaller, so the biggest it could be when n is 1. Negative 1 over n gets bigger, so the smallest it is when n is negative 1, right? So thus, A sub n is bounded. It's bounded above by 1 and bounded below by negative 1, so the sequence is bounded. Okay, so that ends that section.